Welcome to Chapter 6, Properties of Mixtures. We now leave pure materials and the limited but important changes they can undergo and examine mixtures. We shall consider only homogeneous mixtures, or solutions in which the composition is uniform, however small the sample. The component in smaller abundance is called the solute, and that in larger abundance is called the solvent. These terms, however, are normally, but not invariably, reserved for solids dissolved in liquids. One liquid mixed with another is normally called simply a mixture of the two liquids. In this chapter, we consider mainly non-electrolyte solutions, where the solute is not present as ions. Examples are sucrose dissolved in water, sulfur dissolved in carbon disulfide, and a mixture of ethanol and water. We delay until Chapter 9 the special problems of electrolyte solutions in which the solute consists of ions that interact strongly with one another. So, starting with the thermodynamic description of mixtures, we need a set of concepts that enable us to apply thermodynamics to mixtures of variable composition. We've already seen how to use the partial pressure, the contribution of one component in a gaseous mixture to the total pressure, to discuss the properties of mixtures of gases. For a more general description of the thermodynamics of mixtures, we have to introduce other partial properties, each one being the contribution that a particular component makes to that mixture. Throughout this chapter, we draw on the various measures of concentration, molar concentration, molality, and mole fraction introduced in the introduction and in 100-level chemistry. So, starting off with the partial molar properties. A partial molar property, let me grab a pen here. A partial molar property is the contribution per mole that a substance makes to an overall property of a mixture. The easiest partial molar property to visualize is the partial molar volume, or V sub J, of a substance. J, the contribution J makes to the total volume of a mixture. Partial molar quantities are also commonly denoted by a bar over the symbol, as in V bar J, which we see here. We have to be alert to the fact that although 1 mole of substance has a characteristic volume when it is pure, 1 mole of that substance can make different contributions to the volume of a mixture because molecules pack together in different ways in the pure substance than in mixtures. A good example of this, when I was learning analytical chemistry as an undergraduate, we mixed an alcohol component with an aqueous component, and we had measured clearly, arbitrarily, 500 milliliters of each. But when we combined them, the total volume was not a liter, because the two liquids no longer had as much space between the components of those liquids. They packed more tightly together in the mixture than in their pure parts. And that raised questions about how you make a specific target concentration and why so many analytical methods say dilute to 1 liter versus saying adding the difference in water. Because diluting to a liter gives you a final desired volume and / desired concentration versus combining quantities assuming that they will give you a final concentration which you are hope the sum of the 2 components or 3 components. So, moving along, let's take a look at a brief illustration here. Imagine a huge volume of pure water. When a further 1 mole of water is added, the volume increases by 18 cubic centimeters. However, when we add 1 mole of water to a huge volume of pure ethanol, the volume increases only by 14 cubic centimeters. The quantity 18 centimeters cubed per mole is the volume occupied per mole of water molecules in pure water. 14 centimeters cubed per mole is the volume occupied per mole of water molecules in virtually pure ethanol. In other words, the partial molar volume of water in pure water is 18 cubic centimeters per mole, and the partial molar volume of water in pure ethanol is 14 centimeters cubed per mole. In the latter case, there's so much ethanol present that each water molecule is surrounded by ethanol molecules, and the packing of the molecules results in water molecules occupying substantially less volume. And this is just an example, specific example of what I was describing in my experience, which we found iteratively in the laboratory. So moving on, once we know the partial molar volume V sub A and V sub B of two components A and B of a mixture at the composition and temperature of interest, then we should show in derivation 6.1 that we can state the total volume V of the mixture by using the following equation, which we see here, where the volume equals the number of moles of A times the molar volume of A plus the number of moles of B times the molar volume of B. Now, once again, following the trend, this chapter includes a number of derivations, and then there's a lot of value in reviewing the derivation of these fundamental equations. However, for the context of this lecture, we're not going to go through the derivations. We're going to describe them and apply them, the equations themselves. So what I recommend is, as you go through here, once you've seen the content, go back to the derivations as you start to work these problems and see fundamentally where these relationships come from. Or you can, in this particular case, say, well, it makes sense that if you have two components and you're interested in the volume of the sum of those two components, that it would be the partial component in moles times the molar volume, and then sum them. So there's a bit of common sense to this as well, since you have a little bit of chemical experience under your belt at this point. The partial molar volume at an intermediate composition of the water-ethanol mixture is an indication of the volume the water molecules occupy when they are surrounded by a mixture of molecules representative of the overall composition, half water, half ethanol, for instance, when the mole fractions are both 0.5. The partial molar volume of ethanol varies as the composition of the mixture is changed because the environment of an ethanol molecule changes from pure ethanol to pure water as the proportion of water increases and the volume occupied by the ethanol molecule varies accordingly. Figure 6.1 shows the variation of the two partial molar volumes across the full compositional range at 25 degrees Celsius. So if we take a look at figure 6.1 over here, on the x-axis to the left, we see the partial molar volume of water denoted in blue. And on the right, in red, we see the partial molar volume of ethanol. And these two curves overlap one another. And on the x-axis, we see the mole fraction of ethanol in the composition, ranging from 0, meaning there's no ethanol in solution, to 1, meaning the mixture is not actually a mixture, but it's a pure composition of ethanol. And you can see that as the mole fraction of ethanol increases, we have an increase in the partial molar volume of ethanol and a decrease in the partial molar volume of water. So the partial molar volumes of water and ethanol, 25 degrees Celsius, and this is specific to 25 degrees Celsius, of course. Note the different scales where water on the left and ethanol is on the right. So let's jump into an example problem here, using partial molar volumes. What's the total volume of a mixture of 50.0 grams of ethanol and 50.0 grams of water at 25 degrees Celsius? So as a strategy to solve this problem, we're going to use equation 6.1. We need the mole fractions of each substance and the corresponding partial molar volumes. We calculate the mole fractions in the same way as in as we might in the early like Gen Chem type examples, by using the molar masses of the components to calculate the amounts by using N sub j equals M sub j over M sub j, where we have mass divided by molar quantity. So the number of moles is just the mass divided molar quantity. Nothing earth-shattering here. We can then find the partial molar volumes corresponding to these mole fractions by referring to figure 6.1. So, as an example, the molar masses of ethanol and water are 46.07 grams per mole for ethanol and 18.02 grams per mole for water, respectively. Therefore, the amounts present in the mixture are as follows. The number of moles of ethanol are going to be 50.0 grams divided by 46.07 grams per mole. Grams cancel, leaving 1 over 1 moles or moles. So we have 1.09 moles of ethanol present. 50 grams of water divided by 18.02 grams per mole. Same thing, grams cancels, leaving 1 over moles or moles yields 2.77 moles of water. This means that there's a total number of moles of 3.86 moles. Therefore, the mole fraction of ethanol, let me do a little erasing here. The mole fraction of ethanol is going to be 0.282, and the mole fraction for water is 0.718. Remember that you need to use the total number of moles, which is the sum of our two molar quantities, to find the mole fraction. According to figure 6.1, the partial molar volumes of the two substances in a mixture of this composition are 56 centimeters cubed per mole and 18 centimeters cubed per mole, respectively. So from equation 6.1, the total volume of the mixture is going to be as follows. Volume equals 1.09 moles of ethanol times 56 centimeters cubed per mole of ethanol, plus the 2.77 moles of water times 18 centimeters cubed per mole of water, which will give us a total of 110 centimeters cubed, or 110 milliliters of mixture. Now, we extend the concept of a partial molar quantity to other state functions. The most important for our purposes is the partial molar Gibbs energy, G sub J of a substance J, which is the contribution of J per mole of J to the total Gibbs energy of a mixture. It follows in the same way as for volume that if we know the partial molar Gibbs energies of two substances A and B in a mixture of a given composition, then we can calculate the total Gibbs energy of the mixture by using the expression like in equation 6.1. Given that, we can look at equation 6.2a, where total Gibbs free energy is going to be equal to the mole or quantity of A times the partial molar Gibbs energy plus the molar quantity of B times the partial molar Gibbs energy of B. The partial molar Gibbs energy has exactly the same significance as the partial molar volume. For instance, ethanol has a particular partial molar Gibbs energy when it's pure, and every molecule is surrounded by other ethanol molecules, and it has a different partial molar Gibbs energy when it's in an aqueous solution of a certain composition, because then each ethanol molecule is surrounded by a mixture of ethanol and water molecules, and therefore has a different inherent Gibbs energy because of its surroundings and the interactions with those surroundings. The partial molar Gibbs energy is so important in chemistry that it is given a special name and symbol. From now on, we shall call it the chemical potential and denote it with mu. Then equation 6.2a becomes equation 6.2b, where we just simply replace the G sub A and G sub B with mu sub A and mu sub B, where mu sub A is the chemical potential of A in the mixture and mu sub B is the chemical potential of B. In the course of the chapter and the next, we shall see that the name chemical potential is very appropriate, for it will become clear that mu sub J is a measure of the ability of J to bring about a physical and chemical change. A substance with a high chemical potential has a high ability, in a sense we shall explore, to drive a reaction or some other physical process forward. To make progress, we need an explicit formula for the variation of the chemical potential of a substance with the composition of the mixture. Our starting point is equation 5.3b, which shows how the molar Gibbs energy of a perfect gas depends on pressure, and it's shown right here. First, we set P sub F equals to P, the pressure of interest, and P sub I equals P, the standard pressure of 1 bar, remembering that P sub F is our final pressure and P sub I is our initial pressure. So when we go back to this equation, we can see that the Moeller-Gibbs energy at the final state is equal to that of the Moeller-Gibbs energy at the initial state, plus this adjustment factor of RT natural log of the ratio of the final pressure over the initial pressure. At the latter pressure, the Moeller-Gibbs energy has its standard value, which makes sense, it's 1 bar, G sub m. So we can write the following. Where G sub m at pressure P equals G sub m at P initial plus RT natural log P over P sub I. And this is equal to the following. Next, for a mixture of partial gases, we interpret P as the partial pressure of the gas, and G sub m is the partial Moeller-Gibbs energy, the chemical potential. Therefore, for a mixture of perfect gases, for each component J present as a partial pressure P sub J, we can state the following. Or mu sub J equals mu sub J under standard conditions plus RT natural log P sub J over P under standard conditions. And once again, I want you to think of this term that I just wrapped with parentheses as an adjustment factor which corrects from the standard conditions to the conditions we're seeking a solution for. In this expression, mu sub J is the standard chemical potential of the gas J, which is identical, once again, mu is standard chemical potential for any species J, which is identical to its standard Moeller-Gibbs energy, the value of G sub m for the pure gas at 1 bar. If we adopt the convention that whenever P sub J appears in a formula, it is to be interpreted as P sub J over P, so if the pressure is 2 bar, P sub J equals 2, we can write equation 6.4a more simply, as we see below here, where the standard chemical potential of J equals mu sub J plus RT natural log P sub J. So let's take a look here. Figure 6.2 illustrates the pressure dependence of the chemical potential of a perfect gas predicted by this equation. The chemical potential becomes negatively infinite as the pressure tends towards 0. As the pressure is increased from 0, the chemical potential rises to its standard value at 1 bar, and then increases slowly, logarithmically, as the pressure is increased further. As always, we can become familiar with an equation by listening to what it's telling us. In this case, P sub J, or pressure of substance J, increases, so does the natural log of P sub J. Therefore, equation 6.4 tells us that the higher the partial pressure of a gas, the higher its chemical potential. So let's take a look at figure 6.2 here. Note that we, on the y-axis, have our chemical potential, and on the x-axis, our partial pressure. And the variation with partial pressure of the chemical potential of a perfect gas at 3 different temperatures is shown in the ratios of 0.5 to 1 to 2. Note that the chemical potential increases with pressure and, at a given pressure, with temperature. This conclusion is consistent with the interpretation of the chemical potential as an indication of the potential of a substance to be active chemically. The higher the partial pressure, the more active chemically the species. In this instance, the chemical potential represents the tendency of the substance to react when it is in standard state, the significance of the term mu, plus an additional tendency that reflects whether it is at a different pressure. For a given amount of substance, a higher partial pressure gives the substance more chemical punch, just like winding a spring gives a spring more physical punch, that is, enables it to do work. We saw in section 5.1 that molar Gibbs energy of a pure substance is the same in all phases at equilibrium. We can use the same argument shown in the derivation in the text 6.2 to show that a system is at equilibrium when the chemical potential of a substance has the same value in every phase in which it occurs. Restating that. A system is at equilibrium when the chemical potential of each substance has the same value at every phase in which it occurs. Therefore, it's at equilibrium. We can think of the chemical potential as the pushing power of each substance, and the equilibrium is reached only when each substance pushes with the same strength in any phase it occupies. Now, moving on to spontaneous mixing. All gases mix spontaneously with one another because the molecules of one gas can mingle with the molecules of another gas. But how can we show thermodynamically that a mixing is spontaneous? At constant temperature and pressure, we need to show that delta G is less than 0. The first step is therefore to find an expression for delta G when two gases mix, and then to decide whether it's negative. As we can see in derivation 6.3 in the text, when an amount N sub A, or molar quantity of A, and N sub B, or molar quantity of B, of two gases mingle at temperature T, we can see the following, where delta G equals nRT times the mole fraction of A times the natural log of mole fraction A plus mole fraction B times the natural log of mole fraction B, with the number of moles equal to the number of moles of A plus the number of moles of B, and with mole fraction of J, the mole fractions of the components J in the mixture. Equation 6.5 tells us the change in Gibbs energy when the two gases mix at constant temperature and pressure, which we see in equation 6.4. The crucial feature is that because mole fraction A and mole fraction B are both less than 1, the two logarithms are negative. So delta G must also be negative at all compositions. Therefore, perfect gases mix spontaneously in all proportions. Furthermore, if we compare equation 6.5 with delta G equals delta H minus T delta S, or Gibbs change in Gibbs energy equals change in enthalpy minus the product of temperature times change in entropy, we can see the following. From evaluating the structures of these two equations, we can conclude that delta H must equal 0 because the term disappears, and delta S equals negative nR times the mole fraction A log natural log mole fraction A plus mole fraction B log natural mole fraction B, with temperatures canceling as shown. Let's take a look here now at figure 6.4. Figure 6.4, we see Gibbs energy of mixing on the y-axis and mole fraction of A on the x-axis. The variation of the Gibbs energy of mixing with composition for two perfect gases at constant temperature and pressure is shown. Note that delta G is less than 0 for all compositions, which indicate that two gases mix spontaneously in all proportions. So, that is, there's no change in enthalpy when two perfect gases mix, because delta H equals 0, which reflects the fact that there are no interactions between the molecules because they're perfect. There's an increase in entropy because the mixed gas is more distorted than the unmixed gases, which we see in figure 6.5. The entropy of the surroundings is unchanged because the enthalpy of the system is constant, so no energy escapes as heat into the surroundings. It follows that the increase in entropy of the system is the driving force for the mixing. And if we take a look at figure 6.5 here, we see on the y-axis we have entropy of mixing, and on the x-axis mole fraction of A. And it looks like an inverted plot of what we saw in figure 6.4 to the left. The variation of the entropy of mixing with composition of two perfect gases at a constant temperature and pressure is what we're looking at here. And that this entropy is the driving force of spontaneous mixing for perfect gases. Now, let's lead on to ideal solutions. In chemistry, we're concerned with liquids as well as gases, obviously. So we need an expression for the chemical potential of a substance in a liquid solution. We can anticipate that the chemical potential of species ought to increase with concentration, because the higher its concentration, the greater its chemical punch. Just like, analogously, the partial pressure of a gas. In the following, we use the following notation. J denotes a substance in general, A specifically denotes a solvent, B denotes a solute, or A being the major component and B being the minor component of the mixture. The key to setting an expression for the chemical potential of a solute is the work done by the French chemist François Raoult, who died in 1901. So this is, foundational work that happened well over a century ago, who spent most of his life measuring the vapor pressure of solutions. He measured the partial vapor pressure, P sub J, of each component in the mixture, the partial pressures of the vapor of each component in dynamic equilibrium with the liquid mixture, and established what is now known as Raoult's law, which states the partial vapor pressure of a substance in a liquid mixture is proportional to its mole fraction in the mixture and its vapor pressure when pure. And that's shown by equation 6.7. P sub J, or pressure of J, equals the mole fraction of J and its vapor pressure when pure. In this expression, P sub J star is the vapor pressure of the pure substance. For example, when the mole fraction of water in an aqueous solution is 0.9, then provided Raoult's law is obeyed, the partial vapor pressure of the water in solution is 90% that of pure water. This conclusion is approximately true whatever the identity of the solute and solvent, which we see in figure 6.6. Let's take a look at figure 6.6. On the x-axis here, we have pressure, and on the y-axis we have mole fraction of A. The partial vapor pressure of the two components of an ideal binary mixture are proportional to the mole fractions of the components of the liquid. The total pressure of the vapor is the sum of the two partial vapor pressures. The molecular origin of Raoult's law is the effect of the solute on the entropy of the solution. In the pure solvent, the molecules have a certain disorder and corresponding entropy. The vapor pressure then represents the tendency of the system and its surroundings to reach a higher entropy. When a solute is present, the solution has a greater disorder than the pure solvent because we cannot be sure that a molecule chosen at random will be a solvent molecule, which is what we see in figure 6.7. Because the entropy of the solution is higher than that of pure solvent, the solution has a lower tendency to acquire an even higher entropy by the solvent vaporizing. In other words, the vapor pressure of the solvent in the solution is lower than that of the pure solvent. Let me restate that. Because the entropy of the solution is inherently higher than that of pure solvent, the solution has a lower tendency to go to a state of higher entropy because the delta is inherently lower. Yet, when it goes into vapor, it's the same general level of entropy. So, taking a look at figure 6.7, in a pure liquid, to the left, we can be confident that any molecule selected from the sample is solvent. However, when we look to B, when a solute is present, we cannot be sure the blind selection will get a solvent molecule, so the entropy of the system is inherently greater than in the absence of the solute. An ideal solution is a hypothetical solution of a solute B in solvent A that obeys Raoult's law throughout the composition range from pure A to pure B. The law is most reliable when the components of a mixture have similar molecular shapes and are held together in the liquid by similar types and strengths of intramolecular forces. An example is a mixture of two structurally similar hydrocarbons. A mixture of benzene and methylbenzene, or toluene, is a good approximation of an ideal solution, for the partial vapor pressures of each component satisfies Raoult's law reasonably well throughout the composition range from pure benzene to pure methylbenzene, which is what we see in figure 6.8. Let's take a look at that 6.8. On the y-axis, we see the pressure, and on the x-axis, we see the mole fraction of methylbenzene specifically, and we're looking at the trends of the partial contributing pressures of methylbenzene and benzene, and in orange, the total or sum of those two. So for two similar substances, in the case benzene and methylbenzene, they behave almost ideally and have vapor pressures that closely resemble those for the ideal case depicted, which we saw previously in 6.6. No mixture, however, is perfectly ideal, and all real mixtures show deviations from Raoult's law. However, the deviations are small for the component of the mixture that is in large excess, the solvent, and becomes smaller as the concentration of solute decreases, which is what we're seeing in figure 6.9. We can usually be confident that Raoult's law is reliable for the solvent when the solution is very dilute. More formally, Raoult's law is a limiting law, like the perfect gas law, and is strictly valid only in the limit of zero concentration of solute. So let's take a look at figure 6.9, which we see strong deviations from ideality are shown by dissimilar substances, in this case carbon disulfide and acetone. Note, however, that Raoult's law is obeyed by propanone when only small amounts of carbon disulfide is present, which is on the left side, and by carbon disulfide when only a small amount of propanone is present on the right. Propanone, of course, being acetone. And this goes back to that limiting law, which approaches ideality as you tend towards zero. The theoretical importance of Raoult's law is that because it relates vapor pressure to composition, and we know how to relate pressure to chemical potential, we can use the law to relate chemical potential to the composition of a solution. As we show in derivation 6.4 in the text, the chemical potential of a solvent A, present in solution at a mole fraction x sub A, is as follows. Six 8 shows that the chemical potential for A equals the chemical potential for A of pure A, which is the mu sub A with a star, plus the adjustment factor, RT, times the natural log of the mole fraction of A. This expression is valid throughout the concentration range for either component of a binary ideal solution. It is valid for the solvent of a real solution the closer the composition approaches pure solvent, or pure A. A note on good practice: an asterisk is used to denote a pure substance, but not one that is necessarily in its standard state. Only if the pressure is 1 bar would mu sub A asterisk be the standard chemical potential of A, and would then be written as following, with this different term above it. indicating that it's under standard chemical potential. Figure 610 to the right here shows the variation of chemical potential of the solvent predicted by equation 6.8. The essential feature is as follows. Because the mole fraction of A is less than 1 implies that the natural log of mole fraction A is less than 0, the chemical potential of a solvent is lower in solution than when it's pure, inherently. Provided that the solution is almost ideal, a solvent in which a solute is present has less chemical punch, including a lower ability to generate a vapor pressure, than when it's pure. Is mixing to form an ideal solution spontaneous? To answer this question, we need to discover whether delta G is negative for mixing. The calculation is essentially the same for the mixing of two perfect gases, and we conclude that the following: delta G equals nRT times the mole fraction A times natural log of mole fraction A plus mole fraction B, natural log mole fraction B, exactly as for two gases. As for perfect gases, the enthalpy and entropy of mixing are as following. Change in enthalpy equals 0, and change in entropy equals the following relationship, which is summarized above. The value of delta H indicates that although, unlike for perfect gases, there are interactions between the molecules, the average solute-solvent, solvent, and solute-solvent interactions are all the same. So the solute slips into solution without a change in enthalpy. The driving force for mixing is the increase in entropy of the system as one component mingles with another. So, very similar outcomes as we saw for spontaneous mixing of gases. Now, moving along to ideal dilute solutions. Raoult's law provides a good description of the vapor pressure of the solvent in a very dilute solution when solvent A is almost pure. However, we cannot in general expect it to be a good description of the vapor pressure of the solute B, because a solute in dilute solution is very far from being pure. In a dilute solution, each solute molecule is surrounded by nearly pure solvent, so its environment is quite unlike that in pure solute. And except when solute and solvent are very similar, such as benzene and methylbenzene, it's very unlikely that its vapor pressure will be related in a simple manner to that of pure solute. So, leaving off here, to reiterate that, the reason we see divergence in mixtures of solvents when something is at very low concentrations, like the solute would be, is because unlike in its pure form, where it's interacting exclusively with itself and is surrounded by like molecules which dictate a specific suite of weak interactions and potentially of weak interactions. When you put it in a different solvent, unless it's astonishingly similar chemically, it's going to be in a very different environment and have a different suite of those weak chemical interactions. Therefore, it will have an inherently different chemical potential because of that, of being a dilute solute in a different solvent. Now moving back to the text. However, it is found mathematically that in a dilute solution, the vapor pressure of the solute is in fact proportional to its mole fraction, just as for the solvent. Unlike the solvent, though, the constant of proportionality is not, in general, the vapor pressure of the pure solute. This linear but different dependence was discovered by the English chemist William Henry, and is summarized as Henry's law, which is as follows. The vapor pressure of a volatile solute B is proportional to its mole fraction in solution, where the pressure of B equals the mole fraction of B times K sub H, where K sub H which is called Henry's law constant, is characteristic of the solute and chosen so that the straight line predicted by equation 611 is tangent to the experimental curve at mole fraction B equals 0, which we see in figure 612. Let's take a look at that. So on 612 we have vapor pressure on the y-axis and the mole fraction of B on the x-axis, and we see this ideal solution dotted line here, and we have this ideal solution for Henry's law at tangent to the curve of the actual data as it approaches 0. So when a component is almost pure, where near mole fraction of B equals 1, where B acts as its solvent, it behaves in accord with Raoult's law and has a vapor pressure that's proportional to the mole fraction in the liquid mixture and a slope P, the vapor pressure of the pure substance. When the same substance is the minor component, the solute, its vapor pressure is still proportional to its mole fraction, but the constant of proportionality is now K. So, Henry's law is usually obeyed only at low concentrations of the solute, close to the mole fraction equals 0 of mole fraction of B. Solutions that are dilute enough for the solute to obey Henry's law are called ideal dilute solutions. Table 6.1 lists Henry's law constants for some gases. The values given there are for the law written in terms of the molar concentration, where Henry's law, or Henry's constant, K sub H, is commonly reported in kilopascals meter cubed per mole. This form of the law and these units make it very easy to calculate the molar concentration of the dissolved gas simply by multiplying the partial pressure of the gas in kilopascals by the appropriate constant. Equation 612 is used, for instance, to estimate the concentration of oxygen in natural waters or the concentration of carbon dioxide in blood plasma. A known ledge of Henry's law constants for gases and fats and lipids is important for the discussion of respiration, especially when the partial pressure of oxygen is abnormal, as in diving and mountaineering, which we'll discuss in box 6.1. So we see over here in table 6.1 Henry's law constants for gases dissolved in water at 25 degrees Celsius specifically. And let's take a look briefly at this illustration, where we see the concentration of oxygen in water required to support aerobic aquatic life is about 4 milligrams per decimeter cubed. To calculate the minimum partial pressure of oxygen in the atmosphere that can achieve this concentration, we use equation 612 to write the following. Where the partial pressure of oxygen is going to equal K sub H of oxygen, which we can where the concentration of oxygen is going to equal the amount of oxygen at 4 times 10 to the minus third grams per decimeter cubed divided by 32 grams per mole for O2, which gives us the following term, which we can substitute in to 612, where the partial pressure of oxygen is going to equal K sub H of oxygen at 79.2 kilopascals meter cubed per mole, which is what we see here, here, times the concentration of oxygen, which is the term that we developed above, and that will give us our final value. Now let's have a little break from theory and talk about gas solubility in breathing. We inhale about 500 cubic centimeters of air with each breath we take. The influx of air is a result of changes in volume to the lungs as the diaphragm is depressed and the chest expands, which results in a decrease in pressure of about 100 pascals relative to the atmospheric pressure. The expiration occurs as the diaphragm rises and the chest contracts, and gives rise to a differential pressure of about 100 pascals above atmospheric pressure. The total volume of air in the lungs is about 6 decimeters cubed, and the additional volume of air that can be exhaled forcefully under normal expiration is about 1.5 decimeters cubed. Some air remains in the lungs at all times to prevent the collapse of alveoli. The effect of gas exchange between blood and the air inside the alveoli of the lungs means that the composition of the air in the lungs changes throughout the breathing cycle. Alveolar gas is, in fact, a mixture of newly inhaled air and air about to be exhaled. The concentration of oxygen present in arterial blood is equivalent to a partial pressure of about 5 kilopascals, whereas the partial pressure of freshly inhaled air is about 14 kilopascals. Arterial blood remains in the capillary, passing through the walls of an alveolus for about 0.75 seconds. But such is the steepness of the pressure gradient that it becomes fully saturated with oxygen in about 0.25 seconds. If the lungs collect fluids, as in pneumonia, the respiratory membrane thickens, diffusion is greatly slowed, and body tissues begin to suffer from oxygen starvation. Carbon dioxide moves in from the opposite direction across the respiratory tissue, but the partial pressure gradient is much less, corresponding to about 700 pascals in blood and 5 kilopascals in air at equilibrium. However, because carbon dioxide is much more soluble in alveolar fluid than oxygen is, equal amounts of oxygen and carbon dioxide are exchanged in each breath. A hyperbaric oxygen chamber in which oxygen is at an elevated partial pressure is used to treat certain types of disease. Carbon monoxide poisoning can be treated in this way, as can the consequence of shock. Diseases that are caused by anaerobic bacteria such as gas gangrene and tetanus can also be treated because the bacteria cannot thrive in high oxygen concentrations. In scuba diving, where scuba is an acronym for self-contained underwater breathing apparatus, air is applied at higher pressures so that the pressure within the diver's chest matches the pressure exerted by the surrounding water. The latter increases by about 1 atmosphere for each 10 meters of descent. One unfortunate consequence of breathing air at high pressures is that nitrogen is much more soluble in fatty tissues than water, so it tends to dissolve in the central nervous system, bone marrow, and fat reserves. The result is nitrogen narcosis, with symptoms like intoxication. If the diver rises too rapidly to the surface, the nitrogen comes out of its lipid solution as bubbles, just like opening a can of soda, which causes the painful and sometimes fatal condition known as the bends. Many cases of scuba drowning appear to be consequences of arterial embolisms, obstructions in arteries caused by gas bubbles, and loss of consciousness as the air bubbles rises into the head. Now that we had that little segue, let's do an example of verifying Raoult's and Henry's laws. The partial vapor pressure of each component in a mixture of propanone, or acetone, A, and trichloromethane, or chloroform, C, were measured at 35 degrees Celsius with the following results. Confirm that the mixture conforms to Raoult's law for the component in large excess and to Henry's law for the minor component. Find the Henry's law constants. So the strategy to solve this problem, the original procedure was to plot the partial vapor pressures against mole fraction. Raoult's law is verified by comparing the data to the straight line where the partial pressure of J equals the mole fraction of J times the partial pressure of J under normal conditions for each component in the region in which it is in excess, and therefore acting as the solvent. Henry's law is verified by finding a straight line partial pressure J equals mole fraction of J times K sub H, or Henry's law constant, that is tangent to each partial vapor pressure at low molar fraction of J, where the component can be treated as the solute. The modern approach is to fit the data to polynomial using mathematical software and then to use the software to determine the slope and the intercept. So this is not something that you can do easily without some plotting software, but for the solution, let's take a look at what we would see. The data are plotted in figure 613 in the little corner here. The points fit the following fourth order polynomials. Notice, if we take a look over at 613, how the data deviates from both Raoult's and Henry's law for even small departures from mole fraction equals 1 and mole fraction equals 0, respectively. But that as we get closer to those ideal solutions of pure solvent and pure solute, the agreement is substantially improved. Now, Henry's law lets us write an expression for the chemical potential of a solute in solution by exactly the same reasoning as in derivation 6.4, but with the empirical constant Kb used in place of vapor pressure of the pure solute. Partial pressure of B, the chemical potential of the solute when it's present at mole fraction B is as follows, equation 613, where the chemical potential of B equals the chemical potential of B under normal conditions plus the adjustment factor, RT natural log, mole fraction of B. This expression, which is illustrated in figure 614, applies when Henry's law is valid in very dilute solutions. The chemical potential of the solute has its pure value when it's present alone, and a smaller value when dissolved. We often need to express the composition of a solution in terms of the molar concentration of the solute B, concentration B, rather than as a mole fraction. The mole fraction and the molar concentration are proportional to each other in dilute solutions, so we write mole fraction of B equals constant times the concentration of B over C, where C equals 1 mole per decimeter. We shall see that C, the standard molar concentration, equation 613 becomes the following, where instead of RT natural log mole fraction B, we have RT natural log of a new term. We can combine the first two terms into a single constant, which we then denote as chemical potential B, and write this reaction as 614A, which is much more manageable. This equation is the best way to write the relation. However, it is cumbersome, and for the rest of the chapter, we will write concentration of B over C simply as concentration of B. And to conform to the requirements state in the note on good practice, interpret concentration B as the molar concentration with the units deleted. We treated pressure similarly earlier in the chapter, so this shouldn't be too much of a curveball. Thus, if, in fact, concentration of B equals 0.1 moles per decimeter, so concentration of B over C will equal 0.1 with moles removed. From now on, we'll write concentration of B equals 0.1 and use equation 614A in the form of equation 614b, where the mole fraction of B is going to equal mole fraction of B plus RT natural log of the concentration of solute B. Now, figure 615 illustrates the variation of chemical potential with concentration predicted by this equation. The chemical potential of the solute has its standard value when the molar concentration of the solute is 1 mole per decimeter cubed, which is C. right here. And on that note, we're going to wrap this component of the lecture, and we're going to pick up the second half of the chapter in lecture 2. So I'll be speaking to you shortly about that.